the contents of part A. We look at the evolution of wireless networks. And then, most importantly, we will look at telecommunications traffic models. And then in part A3, traffic blocking and throughput that we get through wireless networks. So this is what we are going to do today. Talk about, first of all, wireless network evolution, and then a little bit about telecommunications traffic models. All right. Evolution. I'm having a little trouble in controlling the size of this slide. Here we go. Let me start talking about wireless networks in a sort of a general sense. For those of you who have taken an introductory networks course, you realize that the development of networks is very much organized according to an architecture which is called the Open Systems Interconnection Architecture, or model. And this particular model divides all the interactions that you have to have between a sender and a receiver in a network environment into 7 layers of communications, or 7 relationships, if you like. At the bottom of the 7-layer model is the so-called physical layer. And the physical layer describes basically how you transmit signals and how you modulate a particular carrier with an information signal, and how that information signal is transmitted through a channel that now has a certain effect on the signal. For example, it attenuates the signal, or it picks up interference from other sources. And then you have the receiver, where the receiver tries to demodulate the signal and extract the information that's contained in the signal in the best way possible. So this is the whole point of the physical layer. Then at the second layer of this OSI model is what we might call the quality control layer, where you realize that the extraction of the information from the signal you receive over a channel that is not perfect is not going to be perfect either. So there may be errors that accumulate in the demodulation process, and the second layer basically tries to compensate for that, or tries to give you a method of controlling the amount of this distortion, this error, in various ways. For example, by asking for another copy of the transmission if you detect that there is something wrong with it, or possibly being able to correct any errors that might have occurred through some mathematical manipulation of the received data to find out where the errors are and then undo these errors. And then there are other issues that have to do with quality control. For example, the idea that you don't want to send too much data into a particular receiver that overloads the receiver. So the amount of information transfer in terms of volume and rate has to be somehow matched up between the sender and the receiver. The so-called flow control scheme has to be implemented, and that's part of layer 2. And there are other layer 2 quality control issues that make up the architecture, the OSI architecture. And then at layer 3, we come to the layer where we worry about connectivity. We worry about creating a path, for example, through a distributed network with multiple nodes and interconnecting circuits from a sender to a receiver, and to try to make sure that this particular route, if you like, it satisfies the requirements of the receiver and the sender in terms of information transfer, and in terms of something like information transfer delay values, and so on. So we have the third layer, which deals with connectivity of the network. And those 3 layers, number 1, 2, and 3, really constitute what we call the network protocol layers. Anything above that, layers 4, 5, 6, and 7 are really end-to-end. That is to say, the network doesn't really care about what goes on at layers 4, 5, 6, and 7. It only uses layers 1, 2, and 3 to transfer whatever you give it in the best possible way according to your prescription and according to the capability of the network. So layers 4, 5, 6, and 7 are, if you like, end-to-end. They only involve a relationship between the sender and the receiver. Now, in our course, when we talk about wireless networks, of course, we are only interested in layers 1, 2, and 3. And even more than that, we're not interested really in layer 3. That's more of a higher layer connectivity problem. What we really want to do is look at layers 1 and 2. What is unique about layers 1 and 2 when we talk about wireless connectivity? And so this is where our focus is going to be. So in other words, then, we will look at the design of a signal that carries information over a wireless channel between a sender and the receiver, and how to design the signal in such a way that the effects of the wireless channel can be mitigated or can be reduced or can be controlled in some way. And to the extent that we cannot totally control the effect of a wireless channel, then we have a layer 2 that we will discuss here, where we try to figure out ways of counteracting or ways of, let's say, undoing or mitigating errors that might occur in the processing at layer 1. So we will look at then layers 1 and 2 in the context of a wireless communications channel. The networking itself, how individual nodes are interconnected and so on, that's common to all networks, and we don't need to make a special case of it. But layers 1 and 2 are very specific to wireless communications, and in particular, the channel, the wireless channel, is the one that is going to have to be looked at very carefully, and we need to examine methods by means of which we can mitigate the very bad distortions that wireless channels might produce on our signals. All right, so that's a quick background of where we're heading. Now, if you look at wireless networks, obviously this is a technology that has developed over the last few decades, and it was developed in response to some new technologies that came online that allowed us to control things remotely. So, for example, we now have the idea of a garage door opener. So if I drive up to my house, I don't have to get out of my car anymore. I just push a button on my transmitter and the garage door automatically opens. So I have a wireless communication system going between my device, my garage opening device, and the gadget that hangs on the floor, on the ceiling of the garage. So there are many, many, many applications that have evolved over the years, and wireless communications is the essential ingredient to make these things work. So I have a list here of things that I'm sure you can add to it, and there are obviously many others that go on. For example, when I walk into my office, I pull out my badge and I scan it, and the wireless communication opens the door for me. One of the big things in wireless communications, of course, are the cell phones. So we are now over multiple versions of cell phone technology, and the most recent one being now implemented, of course, the 5th generation cell phones. But that implies that we went through a first and second and third and fourth generation of wireless cell phone technology. There are satellite communications, both for radio, for television, for other things such as GPS, trying to locate a particular device. There are digital cameras now that can transmit information to a line printer. You can control home appliances from your office. You can turn on your heating unit in your home, or your microwave, and so on and so forth. So there are lots and lots of gadgets that require wireless communications. A lot of these, of course, existed before wireless communications, but were connected by cables. And so wireless networks now eliminate the need for cables, which is one of the key advantages of all of this. So now you can sort of summarize what kinds of wireless networks exist. And people, when they think about wireless networks, they think only in terms of cell phones. But cell phones are actually a relatively small part of the whole story. Obviously, radio and television broadcast networks are wireless, and they have been, of course, for many, many decades. But there are other things like fixed wireless access systems where you replace basically cabling with some kind of a wireless communication system. And so, for example, the subscriber lines in ordinary telephone now are no longer copper wiring, but are really wireless communications channels to some kind of a hotspot or a fixed point where the signal is picked up and carried from there on. So there are lots and lots of different types of networks. Cordless telephone systems, you know, my phone in the kitchen hangs on some kind of a receiver and a transmitter, and I can carry the phone around with me throughout the house and the garden and make an ordinary phone call. A key area of development was the idea of wireless local area networks. Now that allows us to communicate between devices that are relatively close to each other in terms of distance. For example, a laptop communicating with a line printer, or a desktop communicating with a line printer, and so on. Or the idea of having devices that allow you to control or turn on and off through some kind of a remote control. Wireless personal area and area networks for short distance interconnections, such as handsets and earphones. And you know, if you have a stereo system, you might have a wireless earphone by means of which you can listen to the CD that you're playing on your stereo system. So there are lots and lots of different networks that have been developed over the years using wireless communications channels. Here's some more. Satellite-based area networks, of course, are also important. For example, they allow you to cross the Atlantic Ocean by making a phone call through the satellite. Or obviously, they allow this GPS technology to be implemented where you can be found where your telephone is, where your cell phone is, and in other ways. So what's the story with these wireless networks? What's good about it? Well, there are lots of things. Obviously, you can move around. You're not tied to a particular location anymore. You have mobility. And then you are independent of where you are in a geographic area. You can be in the mountain. You can be on the ocean shore. It doesn't matter. The connectivity is there. And there's also the idea that the implementation of these networks is a lot simpler than the implementation of wired networks. If you look at wired networks, for example, the amount of cabling that's required to make a connection between two nodes in a network, in a distributed network, is just enormous. And in the case of wireless networks, all you need is some kind of a relay station somewhere 30, 40, 50 miles away from where you are, or where the most other relay station might be. And then it's just a wireless connection between relay stations. So that's much, much simpler. And there are other advantages as well that I haven't listed. But there are also some downsides. Okay. And for example, you might run into a situation where your signal is basically hidden by various obstacles, terrain obstacles, or let's say you are standing on the street corner and a bus moves by you, and the bus may very well obstruct the transport of the signal. So this is a problem that the connectivity is not always 100% the way it is with wired systems. There's another problem here, because in wireless systems you have a problem of sharing the bandwidth among many different applications. The amount of bandwidth that could be available to a particular system may be very limited. And that limits now the amount of data that you can push through such a limited bandwidth system. You know, the rule of thumb is that if you have a bandwidth of, say, a megahertz, roughly speaking, the amount of throughput at a good level of reliability is about the same in terms of megabits per second. So a megahertz bandwidth would allow you to transmit a megabit per second of data through such a channel. Now, different kinds of technologies, communications technologies, have increased that amount. And ultimately, it's a question of how much interference there is in the channel as to how much effective or quality data throughput you can get in a particular piece of bandwidth. But because of different applications having to separate their bandwidth from each other, each application has a certain limit in the amount of bandwidth it can have. So because of the fact that you get interference in these channels from neighboring channels, from other kinds of interference effects such as atmospheric disturbances, you have a high error rate typically, or higher error rate than you might have in some cable-based systems. And that means that generally a reduced quality of service for various kinds of data, voice, and video applications. It may also mean a longer delay. It may mean a limitation in size, weight, and power consumption of the mobile devices. So if you look at your cell phone and it has a tiny little battery in it that has to be frequently recharged, and you can't carry around the cell phone with a large battery because it gets too heavy. So there are these limitations because of portability on the size, weight, and power consumption that you can contemplate. Interference from other systems that share a bandwidth. There is typically this co-channel interference, or interference that has to do with vulnerability. Interference has to do with external systems such as lightning striking your channel and so on. Vulnerability to eavesdropping. Anybody can pick up your signal when it travels through a wireless channel, unlike when it travels through a coaxial cable, let's say. It's a much more difficult type of reading of data when you go through a coaxial cable than when you are transmitting over a wireless channel. I have this experience all the time where somebody in our neighborhood has a garage door opener that operates on the same frequency as mine. And all of a sudden, my garage door opens. So we have this kind of problem that two systems sharing the same frequency, even though they may be spatially separated, the separation may not be enough to eliminate this kind of interference. All right, so these are some of the disadvantages of wireless communications that we have. And now there is, of course, a list of what are the key applications of these wireless networks. Why do we do it? Well, some of these things are quite well known by now. Obviously, the cell phone is probably the primary example of a wireless communications network. But there are many others. For example, there is the idea of telemedicine. So we see that in a case that I personally observed, there was someone in Alaska who had broken a leg. And there was a wireless connection set up, video connection, between a hospital in Los Angeles and that particular doctor's office where that gentleman with the broken leg was located. And the surgeon in the Los Angeles hospital showed the doctor in Alaska how to put on a particular kind of splint for the doctor, for the patient. So this idea of remote telemedicine is quite interesting and has been used in many different applications. So we have a whole bunch of these applications: education, of course, artificial intelligence, travel. You can read that all on your own. Entertainment. We can now download on our iPhone all kinds of audio and video programs. We can watch a movie or we can listen to a CD on the iPhone. We can download newspapers and magazines and all kinds of other things, emails, of course. There's also a question of security. We can try to, or we can figure out how to best protect our passwords and how to transmit usernames in a secure environment. There's some more here: mobile computing, mobile telephony, vehicle-to-vehicle communications, and sensor network applications. That's a key one here. We have, for example, in the Washington area, out towards Northern Virginia, there is a creek. And the creek is being monitored for the quality of the water. And there's a whole bunch of sensors spaced about 100 meters apart or so that measures various aspects of the chemistry of the water and then transmits the reading out to some kind of a collection point where the information can be analyzed. So a lot of this sensor network application is being carried out, and it's of course a lot easier than having to have cables running from each sensor to the collection point. All right, let me go through a quick history of this wide area wireless network development business. And here we talk about wide area wireless networks as opposed to, for example, local area networks. So it started out, as you see here, way back in the really 1990s with the first generation of networks, and a lot of that was based in Europe and North America and Japan. And you can see a list of the different systems that were put in place. For example, the AMPS system in North America, Advanced Mobile Phone System. It was a system that was very narrowband. The amount of spectrum associated with the channel was quite small, and it used analog communications as opposed to digital communications, which we use now. Then we have here a second generation, and the second generation was very important in the sense that it introduced GSM, Global System for Mobile Communications, which in the meantime has become a major system all over the world, with the exception possibly of the United States. In the United States, we introduced the so-called USDC, United States Digital Cellular System, and more importantly, CDMA1, or IS-95, as a second generation network. Then there was GPRS, General Packet Radio, as you see here, and then various kinds of modifications of GSM, such as EDGE, Enhanced Data Rates for GSM Evolution, and the idea of high-speed communications was brought in through this so-called HSC-SD technology. And then IS-95B, which was an enhancement to the second generation network, providing higher data throughput. Then we went on to the third generation, and the major invent there was the CDMA 2000. A single carrier time division multiple access technology was used there, and code division multiple access as well in the CDMA 2000. And again, there were a number of innovations that were brought in through this multiple access procedure called code division multiple access. Then HSPA is a 3.5 generation network, high-speed data access, and the so-called evolved packet system. And that created, again, more data throughput over the amount of bandwidth that was allocated to these networks. We go to fourth generation, where you have long-term evolution as the key technology, and along with that, long-term evolution advanced. And then we had a development in the case of a sort of not local area network, but limited distance networks called Mobile WiMAX IEEE 802.16. And high-speed packet access was an evolution of a previous HSPA, so it's called HSPA Plus, the fourth generation. And now, of course, we are talking about fifth generation networks. And there are three versions. Only one of them really is focused on getting us better telephone service, portable or mobile telephone service. The so-called enhanced mobile broadband is now being deployed, and it's basically an advance over the 4G LTE mobile broadband services. Gets you faster connections, higher throughput, and capacity, and it's intended for areas where there's a lot of traffic, for example, in various kinds of stadiums, or inside of big cities, or even small cities for that matter, concert venues. So it's, in other words, enhancement of the 4G LTE device or technology that has been around for several years now, or actually a decade or so. But there's also the ultra-reliable, low-latency communications version that is for future development, as it's a deployment, as it says here. But again, it's for applications requiring uninterrupted data and robust data exchange. So you cannot have dropouts in the ultra-reliable, low-latency communications version of it. Finally, there's the massive machine-type communications, where you are talking about connecting together a large number of devices, such as millions of sensors that you might be deploying, and that generate massive amounts of data and have to have constant connectivity. So that's the so-called MMTC development, which is still sometime in the future. So this is where we are with respect to the wireless networks on a wide area sense. But there is also the wireless local area network, or personal area network, or broadband area network developments that cover much shorter distances. And the most important one, of course, up to this date is Wi-Fi. Specified in IEEE 802.11 standard. That's what we use a lot to connect ourselves to some kind of a hotspot, to some kind of a point of connection from which the traffic or the signal can be conveyed to other places. There's 802.15, personal and body area networks, so the so-called Bluetooth technology, and that's used a lot in entertainment. And then there is the 802.16 metropolitan area networks, which cover a wider area than, say, Wi-Fi, called WiMAX. And finally, the mobile broadband wireless access, still carrying the signal to larger distances, but at a much broader spectrum, a much higher data rate. So these are the developments that we see here on the local area network or personal area network development. And then we have another issue here, which is cordless telephony. A very important development that makes life inside your home easier. You can walk around with your phone. You're not tied to the chair next to your phone when you want to make a call. You can take your phone with you out in your garden, wherever you want to go. And so there are the first generation cordless telephone systems called CT1, and then there was an enhancement to that, CT1 Plus, and then what we have now is the second generation CT2. So what are we going to do here? Well, we're going to look at some of these systems, these networks, in some detail, but most importantly, what we are going to do is to look at the technology behind these systems. And the technology behind these systems, as I said, is going to be largely focused on layers 1 and 2 of the OSI architecture. So how do we generate signals that can survive in a wireless channel environment? How do we process these signals at the sending side? How do we process them at the receiving side? How do we code information onto these signals so that the information can be extracted at a high quality level at the receiving side? And then ultimately, how do we share the bandwidth of these particular channels with the various applications? And when we look at the applications themselves, we come across the problem of how do we characterize an application? And the application characterization revolves around, first of all, some kind of a traffic model. What kind of traffic does a particular application generate? And so you think, for example, at just two different types of traffic. Let's say making an ordinary phone call. In an ordinary phone call, the traffic, while you are talking from the sender to the receiver, is at a fairly